limits and continuity. So you see where we're headed with this? Limits, continuity, derivatives, integrals. Same sort of thing. Okay, back in Cal 1, when we were given a function of a single variable, and we were asked to evaluate the limit as x approaches a of the function, and we said that that limit actually existed and gave us some answer L, then what we meant by that was that this is a specific example. For this one, if we're looking at, if this is the function f, if we're asked what the limit as x approaches 0 of this function is, we would say it's 1, wouldn't we? And that's because as we approach 0 from both sides, right, the function is headed towards 1, yeah? But we had to check from both sides. All right. Why is this important? Let's continue. What about this right here? This limit would not exist on this function, right? This limit would not exist because, why wouldn't it exist? Yeah, it's not continuous, but does the limit exist? The limit doesn't exist here because your limit from the left and the right are two different things, right? So this limit would not exist. So the important thing in two-dimensional space is that the limit had to exist from both sides. It had to go to the same exact value, right? This is going to be a major problem for us. So if we have a function of two variables, then if we're going to talk about the limit, then what we're going to be doing is we're going to be approaching a point in the domain. So we're letting our xy, our point in our domain, approach some point within the domain, and we're asking ourselves, what is our function doing? Does anyone see why this is going to be a major problem? Why? So let's look at the domain, okay? Here's the domain of our function. Remember, this gets sent through some function, gets sent to a number line, right? So if I say I pick this point AB, and what I want to do is I want to approach that point, AB. What is problematic about that? You can approach it from all sides, right? Not just two directions. I can come in from here, I can come in from here, I can come in from here, I can come in from here. I can come in like this, right? I can come in straight lines. I can spiral into it, right? Any path that you can think of that goes to that point has to be considered. It's not just two sides. And that's a major problem. Because how in the hell are you ever going to test every path heading to that point? You can't. It's not possible. Right? So there's an infinite number of ways or paths that we can approach AB. So if we have to test every path and we know we can't do that, then what's the point, right? Like, what's the point? If we can't test every path, then how would you ever calculate a limit of a function of two variables? Well, we kind of approach it another way. We say to ourselves, it might be easier for us to show a limit does not exist than it would be to show that it does exist, right? To show it does exist, we have to test every path, which seems to be off the table at this point. But we can still check to maybe see if a limit does not. So look at this particular example. I have a function of two variables. The function here is actually f of xy is x squared minus y squared. So to summarize again, what I'm saying is that we are going to be focused on trying to show limits don't exist. Hopefully we'll be able to kind of approach from two different ways and get two different answers. If that happens, we can say the limit doesn't exist. But if we approach from two different ways and get the same answer, then we got to try a different way, and I just said we don't have a way of going through all the different ways. So we're kind of going to hope that it messes up somewhere in the beginning. So here's an example of a function of two variables, and we're asked to find the limit as xy approaches 0, 0. So let's first just check what happens at 0, 0. If you plug 0, 0 into this thing, you get 0 on top, 0 on the bottom. This is undefined, right? So what we need to do now is take the limit as xy approaches 0, 0. So we need to somehow choose a path that heads towards 0, 0. So here I'm going to draw the domain over here. We are trying to head towards this point right here, and we're just going to pick a path. So how about this? Let's head to 0, 0 along the x-axis. Okay? So we're going to come in like this and see what happens. So let's just say I'm going to choose a path here that's going to be the x-axis. So if you're on the x-axis, what can you tell me has to be true about one of those variables? Y is equal to 0, right? If I'm on the x-axis, y is 0. So now what I'd like for you to do is rewrite the limit, and everywhere that you see y, replace it with 0. So limit as x0 approaches 0, 0 of x squared minus 0 over x squared. Isn't that what happens? Now, when you do a limit, you always simplify it algebraically before you calculate the limit. So I'm going to simplify this. What does this become? 1. Okay? So what I can tell you is this. On this surface that's sitting up there, right? We have some surface sitting above the domain. If I come in along the x-axis, my function should be approaching 1. Should we look at it? Yeah, sure, let's look at it. This is kind of hard to see, but let's see if you can make sense out of what I have here. So the orange thing is obviously the surface, right? And I'm going to kind of back the surface out so it doesn't get in our way. So I'm going to kind of pull it back so you can see through it a little bit. The green is the x-axis. And this blue line up here is the function evaluated at every one of these points. So when you plug in that point, it's here. Plug in that point, it's here. Plug in that point, it's here. So as I move along the x-axis, you know, look what's happening. That black dot is my z value, right? What happened there? I got to 0. What happened? Looked like the computer freaked out, didn't it? What happened? Oh, right there. What happened there? I actually let x be 0. And when x was 0, remember this thing is undefined. But that's okay. Limits have nothing to do with what's happening at the point, right? It has to do with what's happening near it. So can you see that what we've done is we were able to get this answer 1 without the picture. We were able to figure out that coming in along the x-axis, our function was always up at 1, or it was headed towards 1. Yes? So let's pick a different path. How about we come in along the y-axis this time? Okay, so if we come in along the y-axis, this is the same as saying that x has to be 0 this time, right? X is exactly 0, so rewrite the limit. Limit as 0y approaches 0, 0. And now look what happens when you replace that. What do you get? Negative y squared over y squared, but that's negative 1. And so if you're approaching 0, 0 along the y-axis, your function's headed to negative 1 now. And that means from 2 different paths, it's headed to two different points, or 2 different z values. And so the visualization of this, again, I'll pull the surface out. The green is us coming in along the y-axis, and you can see now we're down at the bottom. So look at that surface. I mean, can you all see it's kind of a weird shape? I don't know, what does that look like? It reminds me of my daughter comes up to me sometimes with those little finger folder things. Pick a number, Daddy, and it, right? That's kind of, I don't know why it reminds me of that, but that's kind of what we got here. Some weird little fortune cookie shape or something. So we've got this like upper ridge over here, and we've got this lower ridge down here. At 0, 0, it's undefined, but coming in from two different places, two different paths, your z values are headed towards two different things. Not too bad? All right. So what do we say? The end of the story here is that this limit does not exist. Right? The limit doesn't exist because it's got two different answers. All right, let's try that one. So where do you think we should start here? Let's first plug in 0, 0, make sure we have a problem. So if we try and plug 0, 0 in, what do we get? 0 over 0, it's undefined. Okay, so we definitely have a problem, right? So let's pick a path. You want to come in along the x-axis again? Okay, let's do the x-axis. The x-axis means that y is 0. And if y is 0, then this limit becomes limit as x0 approaches 0, 0. And what do we get there? 0 over x squared. And remember, you have to do this computation before you take the limit. What's 0 divided by anything? Anything other than 0. This would be 0. So the limit as we come in along the x-axis is 0. All right? Let's come in along the y-axis and hope for something else. But it's not going to happen, is it? No. As we come in along the y-axis, x is 0. And this time when we do this, we get 0 over y squared this time. But that's still 0. So those two paths check out. They approach the same thing. So we need a third path. What do you want? Any path you want that goes to the origin. Y equals x. I like that one. Y equals x. Now remember, visually this is, we've come in along the x and the y, and now we're coming in along the diagonal. Okay, so let's try that one. So that means I'm going to replace, you can look at this two ways. I'm going to replace every x with y, or I'm going to replace every y with x. It's your choice. So I'll do every y with x. So I'm going to be doing limit xx approaches 0, 0. And then I'm replacing every y with x. So I have x times x over x squared plus x squared. Right? If y is x, then that's what we get. And what does this turn out to be here? The top is x squared. And then the bottom is 2x squared. And then that simplifies to be 1/2. Right? And that means we're done. That means this limit doesn't exist. Because from two paths it was headed to 0, but on this third path, it actually headed to something different.
So if the third path had been 0 as well, it would have been infinitely many.
Well, then we'd have to do a new path, right? I'm going to give you another example where all three of these aren't going to work. I hope you're taking from this that finding the limits of functions of two variables is not easy to do unless the limit doesn't exist, right? If the limit doesn't exist, then we have some hope. I didn't show you the visualization, but here it is. It's kind of almost like a fortune cookie again, but it's kind of got a different shape. So this was in along the x-axis. So can you see that along the x-axis, we kind of ride along this ridge the whole time, and we're at 0. Can you all see that? Even on the back side, we ride along this ridge. And then if we come in the y-axis, we're still riding along that other ridge on both sides. But do you see that diagonal up here? Yeah, that's the part when we came in through that way. There's your diagonal. You can see that took us up to the, up 1/2. So that worked out real nice. So the limit doesn't exist. What about this one? Okay, maybe we can go through this one faster. What if we go in along the x-axis? That means y is 0, right? If y is 0, the top is 0 and the bottom is x squared, and that'll give us 0. Okay? What if we come in along the y-axis? That means x is 0. Okay, if x is 0, we'll have 0 over y to the 4th, which is still 0. So both coming in the x and the y-axis don't work. What if y equals x? Let's try that one again. I'll actually go through that one. If y is equal to x, then you'll get limit, I'll do this again, xx goes to 0, 0, and then we'll have x, what is that on top? If y is x, then that's x times x squared, that's x cubed over x squared plus x to the 4th, right? So x squared plus x to the 4th. What is that going to be here? Yeah, so all you can do here, let me clean this up a little bit. Limit xx goes to 0, 0. Let's factor out x squared from everything. So factor out x squared here, factor out x squared here, and and then they'll cancel, right? So something like that. And now let x go to 0. And what do you get? 0 over 1. So you get 0 again. All right, that didn't work. Man. So maybe you do, y equals 2x, or right, or something like that. Or maybe you try and do some sort of spiral. So we actually have a way of doing this where we can kind of, I'm gonna test an infinite number of paths at one time. Ready? Now here's how I'm gonna do it. We've tested these. Let's look at the ones we've tested. We've come in here. We did a horizontal line. We did a vertical line. And we did the diagonal. But there's a bunch of other lines in here, right, that I could have done? So that's what I'm going to use. I'm going to let y be equal to mx. All right? Where m is some constant. If I change m to 1, that's what we just did, right? If I change m to 2, that's going to give me a slope of 2. 3, 4, 5, or I could even do negative slopes. So when I do this limit, I'm going to get an expression that has m in it, and I'm going to look at that and see if I have any way of making that something other than 0. Let's just work through it and see what happens. I'm going to replace every y that I see with mx. Limit x mx goes to 0, 0 of x times mx squared over x squared plus mx to the 4th. Understand? Okay, let's clean this up. Limit x mx goes to 0, 0. All right, up top we have x to the 3rd m squared over x squared plus m to the 4th x to the 4th. Can we do that same thing we did a second ago? Where we pull an x squared out? Okay, so this will be equal to the limit as x mx goes to 0, 0 of, let's see, what's on top? X m squared over 1 plus m to the 4th x squared. My hope is that there's some value that I can choose for x that will make this thing go to somewhere other than 0. But there's nothing I can choose. Right? I mean, look at this. No matter what you pick for m, right? No matter what the value is for m here, if x goes to 0, that's going to 0, right? And no matter what m I plug here, like this thing's going to 0. Like no matter what. So I still get 0 here. But I've now checked an infinite number of paths. Do y'all see how it's kind of like I'm killing an infinite number of paths at one time? But the problem is there's still an infinite number of paths remaining. Those were just all the linear paths to 0. So no matter what I do, if I approach along any linear path headed towards the origin, there's no way I can avoid my function heading towards 0. So I've got to choose something else. Go ahead.
Y equals mx to the n.
Oh, so you want to go like arbitrary power function. We could do that. To take baby or like smaller baby steps, maybe we can try something like you're suggesting we go to a higher power of x, right? Like instead of doing linear, like let's not approach it along a linear curve or linear path. Let's approach it along maybe a parabolic path. And then if that doesn't work, you go to a cubic and then 4th degree, right? And maybe there's a way you could like eliminate all polynomial power, like all power functions. And then after that, maybe you go and start using sine and cosine. I don't know, but I like your idea, but I do want to start out a little bit more basic. So let's just go with the parabola. You want to try y equals x squared? That means we would be approaching along this path, right? Let's try it. So I'm going to take the limit as x squared approaches 0, 0. So I'm replacing all my y's with x squareds. So what does that become up there? x squared squared over x squared plus x squared to the 4th, right? So what's up top? X to the 5th. I don't want to write this all over again. This is x to the 5th. Then the bottom, x squared plus x to the 6th. The same thing's going to happen, isn't it? Yeah. Like if we pull out an x squared from here and here and here, we're still going to have an x to the 3rd power. Pardon?
X to the 8th.
Where? Oh, yeah, x to the 8th. Thank you. Oof. Number 4 of the day. Man, this doesn't seem to be helping. You want to do x cubed? Try something else. So this didn't work, right? Think we have any hope doing it that way? Instead of y equals x squared, what about x equals y squared? How about if I replace all my x's with y squareds? Let's try it, see what happens. Y squared y goes to 0, 0. So I'm going to replace all my x's with y squareds. What do we get up top? Y squared times y squared over x squared's being x is being replaced with y squared. So y squared squared, and then plus y to the 4th. Oh shit! Look, what do we get? We get an answer other than 0. Because this is now y to the 4th, that's y to the 4th, and that's y to the 4th. So we have 1 y to the 4th over 2 y to the 4th, which is going to be 1/2. Ah, finally, it doesn't exist.
Finally, it
So-
serves no purpose in this realm of existence anymore.
I'm not sure how you get to that other than you continue to take swings at it. But maybe you start to realize that, adjusting the y is not having the impact you want because you're always going to have this term x. You're trying to get a common factor in the top and bottom so that up here you don't get 0 anymore. And so maybe in retrospect, looking back and realizing if that was y squared, you get a y to the 4th here and you'd still have a y to the 4th here. And so your common factor should come out of everything. So again, it's not obvious, but there it is. This one doesn't exist. Yuck, huh?
Yeah.
Here's the picture, by the way. Like, what does it look like, right? Check that out. It's that top ridge right there. You see that top ridge? You follow that around and it keeps you up at 1/2, but if you try and come in any other way, it's going to head to 0. So, squeeze theorem. Remember the squeeze theorem? Cal 1. Squeeze theorem was a way that we could do limits. I'll give you an example. Trying to think of one that would work out pretty nice. Like, think about this limit from Cal 1. Limit x goes to 0, sine squared x over x. Like, what does that go to? Now, you could do that with L'Hopital's rule, couldn't you? So let's just do it with L'Hopital and see what we would get. So if I did L'Hopital here, I do an L here. I know a lot of you that learn L'Hopital, you put H there, but I do L because L'Hopital starts with an L. All right, so we take derivative of the top, so we have to do a little chain rule there. 2 sine x, cosine x, and then over 1, right? And then if you let x go to 0, you're going to get 0. So that limit is 0. But we could also do that using the squeeze theorem. The squeeze theorem says that if you can somehow take the thing you're trying to find the limit of and squeeze it between two functions, I'll call this g of x and h of x. If you can somehow tell me that this is always between these two, and then show me that when you take the limit of this one, that it goes to a constant, and that this one, as you take the limit, goes to a constant and the same constant, that forces this one to also go to that constant. So that was the squeeze theorem. You have to come up with two boundary functions or two bounding functions for the function you're looking at. So the way that I would have approached this with the squeeze theorem is I would have said, all right, I'm going to start with this information. First, I know that sine squared of any value is between 0 and 1. Right? Would you agree? And then what I would do is I'd say, I'm trying to get it to look like that, so I'm going to divide everything by x. And now I've got my middle function, the thing I was looking for. And then this side is 0, less than or equal to sine squared x over x is less than or equal to 1 over x, right? And this wouldn't work. Why wouldn't this work? Yeah, so what I've done is I've said I'm trying to squeeze this between two constants, right? Right now I've squeezed it between 0 and, unfortunately, this one goes to infinity. So all I've done is squeezed it between 0 and infinity, so that squeeze theorem is not going to help me, right? But the foundational idea is that we're trying to squeeze it between two functions, right? Hoping that these two go to the same place. In a function of two variables, we have the same exact idea. If we can somehow take the function of two variables we're looking at, put some boundaries on it, and hope that those two go to the same place when we take the limit, then we can say that the limit exists, so long as they both go to the same constant. That's our only hope, really, to show that a limit exists, is to use something like the squeeze theorem. Because again, you can't check every path. So I have an example here that will hopefully illustrate this going on. So look at this right here. I want us to show that this limit does exist. All right? I want to find this limit. Now you can start checking paths all day long on this. Come in with all these different paths. They're all going to go to the same place. Right? But just because all of them go to the same place does not mean this exists. right? Just because if you check it 1 billion times and every one of them is the same answer, that does not mean the limit exists. But if you can show that this limit exists with a squeeze theorem, then you can say it's the equivalent of checking every path. So I want us to look at this, and I want us to see if there's anything that we can do to create boundary functions on this. Like, is there any way you can bound this for me? And then what we're going to do is try and take the limit of those bounds and squeeze it between. So is there anything you can tell me this is definitely bigger than or equal to? 0. This is a positive number divided by positive plus positive, right? There's no way that this could ever be a negative number, and it is possible that it could be 0. So, right? That's a lower bound. What about an upper bound?
Upper bound wouldn't the upper bound be x squared plus 2y squared?
Say it again.
Wouldn't it be the upper bound be 1 over x squared
1 over x squared plus y squared?
plus 2y?
So what do y'all think about that? Do y'all agree that that could be an upper bound or not? Because we need to all understand why that would be true if it's true.
Yeah. But couldn't x squared be greater than
Could x squared?
middle?
Yeah, so look at this, right? I think what you're trying to get at is that these two match, right?
Yeah.
So the thing that we would need to believe in order for this to be true is that this one has to be bigger than this, right? So is that always true for every value of x and y? Not quite, right? Because that could be like, I don't know, 4, right? And then that would, it could happen that this is, so that's not always going to, but I think you're on the right track. So what could we put? Oh, do what?
Just put x squared over
X squared over
x squared plus 2y squared.
x squared plus 2y squared? Is that what you're saying?
Yeah.
What do y'all think about that? Is that, you'll agree with that?
No, because the signs can also still make it bigger.
But sign's got to be between, well, sign has to be between -1 and 1, right? But then when you square it, it has to be between 0 and 1. So I guess what we're trying to see here is that this is 1, right? How does that compare to this? Like that, this sine squared y must always be smaller than or equal to 1, right? So this is a true inequality. This is correct. However, does it help us? Because what is the limit we're going to take? We're going to let x and y both go to 0, right? So what happens when you get this right here? What do you get when you plug in 0 for x and y? You can get 0 over 0, right? You need these two to go to a constant. In fact, you need that one over there to go to 0 because this one only can go to one place, right? This has to go to 0. So if you're going to squeeze it, you better show me something over here that goes to 0. So although that works, it doesn't get us there. Wouldn't what? Man.
Sorry, I'm trying to think of ways to do this.
Would it maybe be like x squared sine squared y over 1?
So x squared sine squared y over 1. Let's try that. X squared sine squared y. And then here you want x squared sine squared y over 1.
Yes.
So is that true? Is that always true? For all x and y, would that always be true? If you need this fraction right here to be bigger than this fraction, there's two ways to make that happen. Either this numerator has to be bigger than this numerator, or this denominator has to be smaller than this denominator.
Yes.
Right? So these match, right? So in order for this to hold, this has to be smaller than this for all x and y. for all x and y. But I think I could come up with some x's and y's that would make this one smaller than that one. Y'all are getting there. You're running out of options.
I mean, probably do x squared as the points, the point to the distance. So this goes up here.
Or you just do x squared?
Just x squared? Well, let's put it. What about this? Just x squared.
I mean, technically it's still over 1.
Do you want me to go back to that? Or do you want?
No, I'm just saying
Oh.
I don't think that's really worth because then the same problem.
Yeah, I think you're going to run into the same problem here because although this, well, this would have to be smaller than this, but then you also have to factor in this, right?
Yes.
So I don't think that's going to go. Y'all are picking every combination that doesn't work. There's something that does though.
There is, yeah, sure. We just need to get the entire idea of variables. So,
Let me circle something for you. What can you tell me about that ratio right there? No matter what you pick for x and y, other than 0 and 0. What can you tell me about that ratio? It's positive. It's less than 1. Do you all agree that's less than 1? Because x squared over x squared by itself would be 1. So if I tack on any more to it, right, then this thing's got to be less than 1. Or equal to, it could be equal to 1, right? So why don't we just use this? Right? Because this right here is less than or equal to 1. And here's a 1. There you go. So this 1 is bigger than everything I circled or equal to it. And these are identical. And this limit goes where when you let x and y go to 0, this goes to 0. So in the limit that goes to 0, which proves that the middle piece has to go to 0. So you got like on these problems, you just have to kind of mess with it and try and come up with these boundaries and then show it. It is what it is.
like, but what's behind door number 1? Oh, that's not the right one. Behind door number 2. Oh, that's not the right one. You look down the hallway, it's just infinite numbers of doors, just constant and forever internal existence.
Do you all know that there, in our mathematical system, that there are 2 types of infinity? Have you all ever heard that before? Yes? No? No, not that. Not positive and negative. No? How many of you are familiar with that idea? 2 types of infinity? No?
There's like the infinity that ends, because like when you take it's like when you're taking the, like when you talk about the triangle or like triangle, the rectangle, and like that you can split it up into infinite amount of times.
Yeah, yeah.
So it'll give you a number at the end or something like that, right? Is that what you're getting at?
Kind of, maybe not really. I don't know.
What?
So let me discuss it with you. If I just start counting right now, 1, 2, 3, 4, 5, 6, I'm never going to run out of numbers, right? So the set of numbers, well, yeah, the set of numbers, let me do that over. 1, 2, 3, forever, right? That infinite set of numbers is called countable or countably infinite. We know it does not end, right? And we know it does not end, but there's a way that you could count through these numbers, right? Another, well, let me give you an example of an uncountable, all right? So I'm going to do this one visually. So here's the number line. That set of numbers is the number 1, the number 2, the number 3, right? And we're ignoring all the space between them. So we're just going to boop, 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 and count our way through. Infinite set of numbers. Now, if you just look at a number line, and you just look at the numbers, let's just say between 0 and 1, including 0, including 1, everything in between there, everything, and you start counting those, is there a way to count through them? Can you start at 0 and count through?
No.
There's not a way, okay? There's not a way to count through. So it's kind of like here, we can kind of like hop like lily pads across a pond, and as we go, we just take care of each one as we go. If you start at 0 and try and hop to the first number, wherever you think that number is, not only have you missed a number, you've missed an infinite number of numbers. So then you say, oh, I'm going to go back and get one, and then you realize you missed an infinite number there. And so there's just no way to logically move through, systematically, step by step through the numbers. And this is called uncountably infinite. I have a different analogy that might work a little bit better. If you've ever been like far out of the city, way out away from the city lights, you look up in the sky, you actually see stars, right? And you see a lot of them up there. So, you could sit there and just start counting the stars, right? Now, there's not an infinite number of stars, or maybe there is, I guess that's debatable, but you can visualize countable is like that sort of countable. The infinite part, the infinitely uncountable, would be like me asking you to go and try and count the darkness. It's like, it's there, but it's not, you can't put your finger on it. You can't, the only way you can actually get to anything is, does that make sense? Yeah. So there's this famous math problem, not famous, but it's kind of mind-blowing, I think. It has to do with what's called Lebesgue measure when you're first learning about measure theory as a math student. If you just look at all the numbers between 0 and 1, okay, just here we go. There they are, right? And what I'm going to do is I'm going to close my eyes. I'm going to reach in here and I'm going to grab a number. All right, there it is. So what is the probability? What do you think the probability is that I actually have a fraction in my hand? Like, there's fractions in here, right? 1/4, 3/4. How many fractions are in here? Infinitely many. Okay, so I reach in here and I grab a fraction. I grab a number. What's the probability that this is a fraction? What do you think?
1.
So 1 would be 100%?
Yeah.
Okay. Is that my only answer? Does everyone think it's 100%? If you're saying it's 100%, then you're telling me every number in here is a fraction. Right? That's what you're telling me? Yeah. That I have 0 chance of grabbing anything else. Right? Probability that it's a fraction. So in measure theory, which is what we use for all of our mathematics, that probability is 0. Like you have no chance of grabbing a fraction. There's 0 chance. If you reach in there, close your eyes, you reach in there and just grab a number, the probability that that is a fraction, there is a fraction that represents that number, is 0. And the reason why is because the fractions in here are countable. They're like the stars in the sky. What you don't realize is that there's a bunch of darkness between them. So the equivalent thing would be like close your eyes, go out into the middle of this woods somewhere, and point into the sky with this perfect pointer. What do you think the probability is that you are pointing exactly at a star? Like infinitesimally small, right? Does that make sense? Mm-hmm. Yeah. Okay. We are off topic. We are off topic. I have to tell you one more story. I'm sorry, I have to tell you this. When I was in graduate school, and you know what? I don't need this one recorded. on. Now continuity, that's the next thing in line, right? And I think we talked about this the other class, right? I asked about continuity, you remember the definition. This is the definition of continuity of function of two variables. It just says that, hey, in order for us to have a continuous function at a point, we need that the limit exists and that it's equal to the function at that point. So it's like you have this surface, from every direction you're headed to the same place, and at that point you're defined and you fill in that hole. Yeah? So we're not actually going to get into the continuity too much. And the reason we're not going to get into continuity is because we can't even really get our hands around the limit too well. But I will give you this. All polynomial functions of two variables are continuous everywhere. So if you've got a function of two variables that has like x squared y plus y cubed plus 4, as long as it looks like a polynomial, then you can be guaranteed that the limit exists everywhere and that it's continuous everywhere, which is nice. Also, all rational functions are continuous on their implied domain. So every function that I've given you, that we've had a fraction, you know, we've had some problems where we had 0 over 0, but everywhere else where you didn't have 0 over 0, it is continuous. And then anytime you take the composition of two continuous functions, you are still continuous. So these things are kind of following what happened in Cal 1. And that's it. So there's not many problems with it in this assignment. It's just a few, and it's just like, hey, you know, show the limit doesn't exist. So you try these different paths, and I believe there's one in there where you're going to have to try and do a squeeze theorem. Cranking along. Let's see, where are we at? 11.3? That was 11.2, right? Yeah, 11.3. Let's see, let me check the calendar real quick. We still have a lot of time, so I'm not going to stop, but let me just see where we are. Yeah, let's do this. I'm trying to make a little more time for later, because the concepts later are much more difficult. So the more stuff that we can get in now, the easier time we'll have later. We won't be trying to grasp difficult concepts because, you know, with having such a long class, there's going to be a point in time where I introduce a topic, and then by the end of class, it's like you're supposed to have mastered that topic. You know, so we want more time for that so that you can actually get home and do problems and spend. So I think this is one of our first really cool visual ideas. So we have this idea of a partial derivative. So remember in Cal 1, we all know what the derivative of a function was, right? It's the slope of the tangent line. What do you think is going to be a problem if I want to try and talk about the slope of a tangent line on a surface? What do you think fundamentally is going to be an issue? Like, imagine yourself standing on this surface, right? And I ask, hey, at that point you're standing on, what's the slope of the tangent line? What do you think fundamentally is kind of wrong with that question? It depends on which way you're pointing, right? Like this surface, you're standing on it. Slope of a tangent line, like here, if I'm on the function, there is only one tangent line. It's the one that goes like that. But on the surface, it kind of depends on which way you're aiming. And so the partial derivative idea comes from trying to figure out a way to answer that. So this is, let's kill the lights a little bit so that you can see this a little better. Excuse me. So we have this surface. I'm going to come back here so I can see it myself. So we have this surface. Where's my box? Make it a little bit bigger. All right, my x-axis is coming out this direction. My y-axis is coming out this direction. There's my z, and I'm just on this surface. Let me try and move that point. Oh man, it messed up my zoom. Try and move that point where you can see it there. Everyone see that? All right, so if you're standing right there and we want to talk about the slope of a tangent line, one thing we could do is come through and slice this surface with a plane. So what if I fix my y value? In other words, let y be whatever my y coordinate is, cut through with the plane that's got a fixed y value. So it's parallel to the xz plane, right? If I do that and then kind of change my point of view from the side, so I'm going to take the surface out. If you take the surface out and now you're kind of looking from the side now, do you see that we're kind of back in Cal 1 now? And this is just, we can find the slope of that tangent line. But we had to fix our y value to be constant in order for that to work, right? But we could have also fixed our x coordinate to be constant. So let me do that. If I fix my x coordinate, this plane is parallel to the yz plane. And if I look at it from the side here, again, I'm back in Cal 1. So this section has to do with partial derivatives, which are these two scenarios where we look at it and try and calculate the slope, that red slope right there, or we cut it the other way and try and calculate that slope. So we're only going to be looking from two directions. Later on, we'll allow ourselves to rotate to any angle and look at the slope in any direction, all right? But for now, the partial derivative is just going to handle two directions only. So we need to get some notation down. So the first thing is if z is some function of x and y, if we hold our y constant, so I want you to try and, other than what I put up there, visualize this like right here in the room. Remember, x is this way and y is this way, right? So if I'm holding y constant, I'm going out to some point, I'm standing on the surface, I'm holding my y constant, right? That's this direction. That means I'm facing like this or like this, and I'm basically trying to walk that way. I'm either going to be going up or I'm going to be going down as I walk, right? That is called the partial derivative with respect to x. So when you hold y constant, you're allowing x to vary, and that's called the partial derivative with respect to x. And the way we denote it, we don't use that prime anymore. We do a subscript. So this is what we used back in Cal 1. We used that prime. And that's because we only had one variable we only had one variable, right? So the derivative can only have one meaning. But the fact that we have two variables now means that we can hold one of them constant and leave the other one as a variable, and we need to be specific on which one is going to still be a variable and which one's constant. So this has to be the notation. Now if we do it the other way around and we hold x constant, this time we walk out there, we go here, we get to our point, we're going to hold our x coordinate constant. So now I'm facing like this, and I'm going to walk either this way, up or down, depending on what I get. All right? So the notation there is a subscripted y. So when we say you hold something constant, what we mean is that it's actually being held at a number. We're not telling you what the number is, but we're saying it is basically essentially a number in the problem. So on this problem, we're going to be able to just practice taking partial derivatives. So for part A, we want to find the partial derivative of f with respect to x at the point 2, 1. So it's like if I go out 2, I move over 1, and I look that way, am I going to be going up or down? So I need to first calculate what is the partial derivative of f with respect to x. So what am I holding constant here? Nope. Y is being held constant, okay? So let's go up to the original function, and everywhere I see a y, I'm going to imagine that it's a constant. So what would the derivative of y cubed be? 0, because y is a constant, right? So imagine that y is the number 2. 2 cubed is 8, derivative of 8 is 0. So that goes away. Plus, now, what's the derivative of 2x? That's just 2. All right, so that we're treating just like we did before back in Cal 1. Now this one here is a little bit tricky.
That's good.
2x, but what about the y to the 5th? Yeah. So do we use product rule or do we not need product rule? What do we do here? Let's just look at it real quick over here. Remember, this is like a constant, isn't it? So if I said a constant times x squared and asked you for the derivative, you would just bring the constant along. You wouldn't do anything with it. So the 2 is going to come out here and you'll just have 2x, but you'll still have the y to the 5th. So this next piece right here will be plus 2x y to the 5th.